Welcome students to our video notes lesson on section 1.7. In this section we are going to revisit the idea of factoring, but we're going to be looking at expressions that are not necessarily quadratic, meaning having a highest exponent of 2, which is why we're calling this polynomial factoring. So the question might be, what is a polynomial? So I have kind of a definition here, but let me kind of explain it. I would like you to also write these words on your outline as you're listening. So your outline has a couple of lines here for you to write some of this down. Please add this to your outline as we go. So first of all, in this word polynomial, you see it begins with this first part, this prefix of poly. And that word poly means many. So it's many of these nomials, or monomials, I should say. So a polynomial is when you're adding or subtracting. A sum could mean subtraction if you're adding a negative. So it's the sum of, or adding or subtracting, one or more monomials, or sometimes we call monomials terms. Now a monomial is when you have only one. So this word mono means one. And it's one product of numbers and variables. So for example, it could be something like x squared. That could be a monomial because it's just the product of x and x. And it's just one product, right? Just one product. I'm just multiplying one time. Or it could be something like 5x because that's a product of a number and a variable. So one product, it's a monomial. Or it could just be a single variable like x, or just a single number like 5. It doesn't have to be a product, but it could be. Now a polynomial is when you take one or more of these products here and add them together. So just take a quick look down here at the examples I have. So maybe x squared plus 5, right? I'm adding this product of x and x with this single number. So this one here is a polynomial, one or more monomials. Here I have a product of numbers and variables minus another product of a number and a variable plus another number. So this would be a polynomial with 3 terms. Because I'm adding and subtracting them, it's a polynomial. Here I have 4 terms. X cubed, which is my first term, plus, right, that's the sum. 2x squared is my second term, minus, you can think of that as adding a negative, so it's still a sum of 5 times x, and then plus 4. So each of these single things, 1, 2, 3, 4, each of those are monomials, and then when you add and subtract them to each other, that makes a polynomial. Now a polynomial could have exponents that go higher than 2. So this is kind of a generic one right here, and I start with an exponent of n, and then I count down, n minus 1, dot, 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 all the way down to x to the first power. First power is the lowest power because, let's see here, in this last term, technically it's x to the 0 power. But x to the 0 power is equal to 1, which is why you don't see it written there. So technically you count all the way down to the 0 power, except the last one you'll see is a first power. Right here you just see x to the first. Here you just see x to the first. But usually we begin with the highest exponent. So these n minus 1, and 1, those are the exponents, and they can go higher than 2. And that's kind of what this video is about. It's dealing with polynomials where the exponent at the beginning, or anywhere really in the expression, might be higher than 2. It could just be 2, but it might be higher than 2, like 3. These parts here, the a sub n and the a sub n sub 1 and the a sub 1, those are just representing the numbers in front, the real number coefficients. So those would be representing like this number 1 right here, the 5, the 6, the negative 3, the 1. It's all the numbers in front of the variables. That's what these guys are. And then of course x represents your input, your independent variable, the place where you would plug in something to evaluate these expressions. So what we're going to look at in this video is how to factor expressions that may have an exponent higher than 2, but that are still considered polynomials. So they may not be quadratic, but they are still polynomials, and there may be a method for factoring them by hand. One such example are these down here, the sum and difference of cubes. This is a very special type of factoring because there's a formula that helps us do it, but it deals with cubes. So it deals with when we have exponents that are 3, or they could be some kind of multiple of 3. So we're dealing with higher exponents, so we can't really call it a quadratic. We can call it a polynomial. So that's why we began this lesson with the definition of a polynomial. So let's just take a look at this very specific type of polynomial. This is a very specific type of polynomial. We don't need to worry about this sort of generic example here. We just want to think about this very specific type. So when I say specific, I mean, notice that in each of these expressions, there are only 2 terms. So it starts out with either adding 2 terms or subtracting 2 terms. So that's very specific. And both of the terms have to be perfect cubes. That is also very specific. So I have 2 terms only. Both of them are perfect cubes, a cubed, b cubed, a cubed, b cubed. And I'm either adding them, that's the sum, or subtracting them, that's the difference. Very specific. So before we look at the formula, let's just take a look at what that looks like in our examples. So look, I have 2 terms. Both of them are perfect cubes. 2 terms, both of them are perfect cubes. That is what's going to tell you, wait a second, this is a special, specific type of polynomial with a specific factoring formula. Next, let's take a look at the formulas. The formulas are right here. When you have something of this form, 2 terms that are being added and they're perfect cubes, you're going to have one answer with 2 terms. Notice how it's a and b. Then you'll have another answer with 3 terms. A squared, ab, and b squared. That is the same for both of these. A squared, ab, b squared. ab, a squared, ab, b squared. Now let's look at the signs. For the sum of cubes, the first factor is adding. So that sign is the same as the original expression. The original expression was adding, so the first factor is adding. Then if you look at the second sign, it's subtraction, so it's the opposite. The opposite from what the original question was. And then this last one is always positive, because it was a plus here when it was a sum of cubes, and it's a plus here when it's a difference of, so it's always positive. Notice again with the difference, it started as a subtraction, so then the first factor with a and b has a subtraction, so that's the same sign as the original expression. And then the middle term changed to a plus, so that one was the opposite sign. So when you look at these signs, we have the same sign, so I'm going to use S, the opposite sign, I'm going to use O, and then always positive. So that's AP. When you put those letters together, it spells the word soap. So a lot of times I'm going to say, oh, use the SOAP formula. Same, opposite, always positive. What I'm referring to are these formulas here. This is what the factors will be made of when you have a sum of cubes or a difference of cubes. Now before we start using this formula, I want us also to take a look at some perfect cubes, because in order to recognize that it's a sum of cubes or difference of cubes, you have to be able to recognize that the numbers are perfect cubes. So let's just go through some of these and determine what they are when you cube them. Now remember, to cube a number means you multiply it to itself 3 times. So 1 cubed is just 1. So you know what? You're going to have to really pay attention to the 1, because a lot of times students don't think of it as a cube, but it is a cube. It's its own cube. So remember that. 2 cubed would be 2 times 2 times 2, which is 8. 3 cubed is 3 times 3 times 3, which is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. You see that number right here. That's what you get if you do 8 times 8 times 8. 9 cubed is 729. And 10 cubed is 1,000. So I want you to really kind of make note of these numbers. These numbers are perfect cubes. And when you see them in a polynomial, I want you to go, wait a second, that is a perfect cube. Okay, so we have our list of perfect cubes up to 10 anyways. We have our formulas for factoring. Now let's take a look at how this works. In number 1, we have 2 terms. So that's what I would want you to notice first of all. I want you to notice that there's 2 terms. The second thing I'd want you to notice is that the first term is cubed. So that should be an indicator that maybe this is a sum of cubes. The third thing I want you to notice is that they're being added, which makes it a sum. And then the last thing I want you to notice is that 512 was 8 cubed. That was what we got when we did 8 times 8 times 8. So we could think of this as x cubed plus 8 cubed, because that's what 512 is. So this looks a lot like a cubed plus b cubed, where a would be x and b would be 8. X cubed, 8 cubed. So it's a sum of cubes where a is x and b is 8. So the formula for that, we start with a and b, and we use the same sign. Remember, SOAP. So this was plus, so this will be plus. And then it's a squared, ab, b squared. We do the opposite sign, so since that was plus, this is minus, and then always positive right here. Now in this scenario though, it's not x, it's not a cubed, it's x cubed, and it's not b cubed, it's 8 cubed. So remember, the a here is x, and the b here is 8. Okay, so x cubed plus 8 cubed would be a plus b, or x plus 8. Same sign. And then x squared, and then opposite sign, and then a times b, so x times 8, although we'll probably write it as 8x. And then b squared, so 8 squared. Except for your final answer, I want you to write that as 64. So I want you to write it this way. X cubed plus 512, but remember that was 8 cubed, is equal to the factors of x plus 8 times x squared minus 8x, and then let's multiply this out. 8 squared is 64. This would be your final answer for the factors. Now, I'm not going to make you do this in your classwork, but for the sake of learning, we're going to check. We're going to multiply these together and see if it actually does somehow magically equal x cubed plus 512. So I'm going to multiply these together because that's what it means to factor something. It means that you are breaking that thing, you're breaking this expression into the 2 factors that multiply together to equal this. So to see if we did it right, we can multiply them together and see if it equals this. So I'm going to do x times x squared, that's x cubed, so far that checks out. X times negative 8x would be negative 8x squared, because I did x times x. X times 64 would be 64x. So I did my first distribution. Let's do the second distribution. 8 times x squared, that's 8x squared. 8 times negative 8x would be negative 64x. And 8 times 64, that would be 512, because it's 8 times 8 times 8. So look at this. Notice how I had a positive 8x squared and a negative 8x squared. So when you add those together, they cancel. I had a positive 64x and a negative 64x. When I add them together, they cancel. And all you're left with is an x cubed and a positive 512. So it's really true that when I multiply these 2 together, I get this. So these 2 things really are the factors for x cubed plus 512. Again, you don't have to do the checking when you're practicing. I just wanted to show you just this one time so you can see that these long factors really do end up canceling out a lot of stuff to end up with just an expression with just these two terms. Now let's try it again with number 2. Okay, so first we notice that there are two terms, because not all of our polynomials have only two. There's only two terms here, 1, 2. Second thing we notice, x is cubed. So that's a trigger. Maybe this is a difference of cubes, right? Third thing we notice is that it's subtracting. So that's a difference of cubes, not a sum. And then the last thing we notice is that 125, that's a perfect cube of 5. That was right here. And 64 is also a perfect cube of 4. That was right here. So that makes us think about this formula, a cubed minus b cubed. And that is a minus b times a squared plus, that's the opposite sign, ab, and then plus, always positive, b squared. In this case, though, let's take a look here. I want to think of the 125 as 5 cubed, and then the x cubed is x cubed. So I can think of 125x cubed as 5x all cubed, because 5 cubed is 125 and x cubed is x cubed. And then the 64 I can think of as 4 cubed. So when I'm trying to match it up to the a cubed and the b cubed, I could say, well, a is 5x and b is 4. And it's 5x cubed, that's a cubed, minus 4 cubed, which is the b cubed from the difference of cubes formula. So then we would say this. We would say 5x cubed minus 4 cubed would be a minus b. A is 5x, b is 4. So it would be 5x minus 4. A squared, that would be 5x squared. Because remember, in this particular situation, the first term cubed was 5x cubed. So that's 5x now squared, according to the formula. Plus a, that's 5x, times b was 4. ab, 5x times 4. Plus b squared. b was 4, so 4 squared in this example. That's 4 cubed, so b is 4. Okay, I'm going to simplify this a little bit, and I'm going to write it this way. Instead of writing it as 5x cubed, even though that's what it is, I'm going to write it back the way it was. 125x cubed minus 64 is equal to 5x minus 4 times 5 squared, 25x squared, plus 5x times 4, that's 5 times 4, 20x, plus 4 squared, that's 16. According to the difference of cubes formula, this would be the answer. These two things here would be the factors of 125x cubed minus 64. And it was based purely off this formula way up here in our notes. So what you really need to do is memorize this formula, and I'm hoping that this acronym of SOAP will help you do that. Now sometimes, like in example 3, you're going to have what's called a GCF. You're going to have to take out a greatest common factor first before you can recognize what the perfect cubes are. So what I want you to do here is notice that there are only two terms and x is cubed. But the numbers of 2 and 54, those aren't perfect cubes. That must mean there's a GCF I need to take out. I notice I can divide both of these numbers by 2. So I'm going to factor out a GCF of 2. And when I do that, I'm left with just x cubed minus 27, right? 54 divided by 2 would be 27. So now notice 27 is 3 cubed, right? And x is cubed. Just keep in mind I'd have to have this factor of 2 outside of my final answer as well. So this is a difference of cubes, right? We're subtracting, so notice that it's subtraction, which is a difference of cubes. So I'm going to use this formula, the a cubed minus b cubed formula. Okay, now in this scenario, it's x cubed. So again, a is x, and it's 3 cubed, right? 27 is 3 cubed, so b is 3, right? It's x cubed minus 3 cubed, 27. So, according to my difference of cubes, a minus b would be x minus 3. A squared would be x squared. ab would be x times 3, but we write that as 3x. And then I'd have 3 squared. So that would be x minus 3, x squared, plus 3x, plus 9. That's the difference of cubes part. That's this part. But don't forget that we had the 2 in front, our GCF. So our final answer for number 3, so we had, remember it started out this way, 2x squared minus 54. We began by factoring out the 2 and recognizing that the 27 was a perfect cube. So then we used the difference of cubes formula to get the factors, but the 2's still there, and it's being multiplied to these 2 factors. So it's 2 times x minus 3, I should use the simplified form, times x squared plus 3x plus 9. These are the 3 factors that if I multiply together would equal 2x cubed minus 54. Now, what I'd like you guys to do is I want you to try number 4. You try this one, check your answer, see if it's right. If not, watch the video to get the right answer and then go back and enter in the correct answer. Okay. So these are the final factors you should have ended up with. You should have had one factor of 2x plus 9 times a second factor with 3 terms of 4x squared minus 18x plus 81. This is because 8 is 2 cubed. So the first expression can be thought of as 2x cubed. And 729 is 9 cubed. So the second expression can be thought of as 9 cubed. So the a, so to speak, was 2x and the b was 9. So I just plugged those in where the a and b go in our formula and simplified from there. So the purpose of these last examples is to show you the different things that can happen when you are factoring polynomials. So as we've seen, when we factor out a GCF, sometimes it's still possible to factor further. We should always check and make sure that we have factored completely. Factor completely means that there's no other way to break it down any further. We have broken it down into its smallest possible factors, or sometimes we refer to them as prime factors. So taking a look at number 5, this is a situation where we would start by taking out a GCF. So I'd start by noticing each term here has an x. So I would take out an x. And that means each term would now have one less x. So this would now be x to the 3rd instead of the 4th, plus 11x squared instead of cubed, minus 4x instead of x squared, and then minus 44. So we do that, but we're not done yet. We can keep going. This is a situation where we could factor by grouping. So I want you to notice that there are 4 terms. And you can, when you have 4 terms, you can factor by grouping. So factoring by grouping is where we split these up into 2 parts. So we have the first pair is x cubed and 11x squared. And then the second one is negative 4x and negative 44. And we look at a GCF of each pair. So this one I notice I have at least 2 x's in each term. So I'll take out x squared. And then I'd be left with x plus 11. In this one, I notice I have a negative in common with both and a 4. So I'll take out a negative 4 and I'll be left with positive x plus 11. I notice I have the same factor in my 2 parts. So now what I do is I factor out that common factor. So I have x plus 11 is my common factor, and then my remaining terms are put together as the second factor. Don't forget about my GCF, that was in the beginning. So I have these three factors, but, notice here, this is a difference of squares. This was our last video. Difference of squares. It has two terms that are both perfect squares that are subtracting. So this follows this formula, a squared minus b squared, which equals a plus b times a minus b. In this situation, a would be x, right? This is x squared, and b would be 2 because 4 is equal to 2 squared. So I can factor this into x plus 2 and x minus 2. So my final answer for number 5, I'm going to write it over here, was my GCF from the beginning, x, times my times the factor of x plus 11, times the two factors from x squared minus 4, which were x plus 2, x minus 2. So notice I was able to get 4 factors for this polynomial by using our techniques of taking out a GCF, factoring by grouping, and using the difference of squares formula. Now in number 6, this is a situation where we might notice, oh, this looks like a difference of squares. So we might say, okay, because I could think of this as m cubed squared minus 8 squared. So it's a difference of squares. So it could maybe use this formula, which factors into a plus b and a minus b. In this case, a would be m cubed, because m cubed squared is m to the 6th, and b would be 8. So this could factor into m cubed plus 8 and m cubed minus 8. Okay, I did my difference of squares, done, except now I have 2 sum of cubes and difference of cubes. This one looks like an a cubed plus b cubed, and this one looks like an a cubed minus b cubed, because 8 is 2 cubed. So we notice, okay, this is a sum of cubes and a difference of cubes. So I need to factor both of these using the formulas. So I have to use the sum of cube formula, which is a plus b, a squared minus ab plus b squared. And I have to use the difference of cubes, which is a minus b, a squared plus ab plus b squared, where a is m, because it's m cubed, and b is 2, because 8 is 2 cubed. So here we go. So the first one, the m cubed plus 8, that would break into m plus 2, and then m squared minus 2m plus 2 squared, which is 4. And then the m cubed minus 8, this one here, would break into m minus 2, and then m squared plus 2m plus 4. So that's my full answer for number 6. Isn't that crazy? Something so simple. It was just these two terms, m to the 6th minus 64. But when you factor, it factors into 1, 2, 3, 4 factors, and 2 of those factors have 3 terms. This one's crazy. Just be like, guys, what's going on here? That's crazy. But it can happen. So always make sure that you have factored all the way. Check for things like difference of squares. Check for things like sum and difference of cubes. Last but not least, we're going to just do one last example. So this one, I'm noticing again there is a GCF, a greatest common factor. I notice each term can be divided by 2 and x. So what I'm going to do is start by pulling out a 2 and an x from each term. So this one would have 3x squared. This one would have minus x. This would have minus 10. I took an x out of each and I divided each number by 2. And what I notice is I have a trinomial, a quadratic, right, x squared, trinomial that I could maybe factor using the methods from section 1.5. So I'm going to do that now. I'm going to try the 3 times 10. That gives me 30. And then there's a negative 1 in the middle. So I want to look for two numbers that multiply to 30 and at the same time add to -1. So I notice that I can use -6 and +5 because if I add them together, I get -1. So what does that mean? That means I can keep going because it worked. I was able to find two numbers that multiply to -30, excuse me. This should have been -30. I was able to find two numbers that multiplied to -30, -6 and 5, and those same two numbers added to -1. So we split the middle term into -6x and +5x. So I use these numbers. And then I drop down the -10. This is from section 1.5. Don't forget the 2x is still there on the outside. I might kind of ignore it for a little while, but don't forget it's there being multiplied to this. And then I factor by grouping. So I'm going to go ahead and take out a 3x from this group, and I get x -2. I'm going to take out a 5 from this group. I get x -2. And then I notice I have a x -2 in common, so I can factor that out. And I have remaining factors of 3x and 5. And then don't forget my GCF from before, right? That has to go out in front. So my final answer had three factors: 2x, x -2, and 3x + 5. If I were to multiply these all to each other, it would end up equaling this expression right here. So these were some pretty tough factoring problems, and so we'll be practicing them in class, and I look forward to seeing you there.